Thank you so much for these nice words, and thank you so much for the invitation to this conference. It's also a pleasure to see, or I would like to highlight two different things. So I think this is the most female conference held ever in Bergen. So I think that's great. And I also welcome the men present, and we also hope to attract more men to the field of nutrition in the future. So you are especially welcome, and also it's a pleasure to see so many former students and collaboration partners all from Norway. So welcome, a warm welcome to everybody who is either coming back to rainy Bergen or here visiting the conference. I would also like to bring greetings from the head of the Center of Nutrition, Gülen Arslanli. She is traveling to Turkey right now, so she cannot be here. But I would like to send her greetings also to the conference. Yes, I think we had a very nice introduction into the topic, and this really touched the core of nutritional science or dietetics. So how do we know about what people are eating? And we have learned, at least I have learned, that we have a lot of challenges in this field, but on the other hand, there are also light at the end of a tunnel, or light at the horizon. So that's also quite good. And something that can bring even more light to the horizon is the inclusion of dietary biomarkers, and I would really highlight today the biomarkers of food intake. So, because dietary biomarkers is a very broad field, and I really would like to go on the food biomarkers. When I prepared this lecture, I came across a very nice viewpoint from Frank Hu and Walter Willett, which they published in November last year in the Journal of the American Medical Association. I can strongly recommend to read that, and I have several quotes of this statement. And so they actually said that we also have heard right now that human diet is a complex, dynamic exposure with no perfect methods to quantify all aspects of dietary intakes and eating behaviors. And I think that really summarizes the challenges that we focus not only in research but also in clinical practice and in daily practice with clients and consumers very, very, very clearly. So this is really something that I would like to highlight in the beginning. And so what is my presentation all about? So we will talk about this dietary biomarkers, so what it is, what we need to get reliable data on dietary biomarkers, and also different approaches to identify dietary biomarkers. And here it becomes already very clear that this is a really multidisciplinary and interdisciplinary area of research. So we need really to collaborate with different fields, and I would really like to highlight this need, and that we can really get a lot of beneficial inputs into the field of nutrition research and nutrition practice. And then I will like to present some examples, and these are really more or less random taken. So there could be a lot of different, but I could also talk a whole week about all these different examples. So I had to limit myself a little bit, and then we will draw some conclusions. So what are actually dietary biomarkers? And why do we need them? So we need them, and that I think we have heard already very nicely, that we have these complex chronic diseases, and usually they have some association, or some less strong, some modest, some strong association with diet. But this is very often difficult to establish. Think about that. For example, in cross-sectional analysis, we very often do not see any association between sugar intake and obesity. And this is probably due to measurement errors, and not due that there is no association between sugar and obesity. We have I don't have to discuss with the next point, that dietary assessment are prone to random errors and systematic biases. And also, if we look to recent intake data, both from national surveys, not only in Norway, but also in many other different countries, we know that people are really not following the dietary guidelines. And we would like to identify these people who are not following the dietary guidelines. So we would like to know about that. And the dietary quality of many people may still be poor, even though we have so many choices. I think the choice of foods has never been as abundant as today, but still people choose also a lot of junk food, a lot of food that has an unfavorable composition, and so we would like to guide them, and we would also like to know about this. So what we really like to do is that we would identify biomarkers of food intake that can assist or improve or even replace the cumbersome dietary intake assessment. So that would actually be something that would be perfect. If we had biomarkers that could say this person, measuring some whatever biomarker in blood or urine, and say this person ingests like 100 grams of sugar a day. That's something unrealistic, but that would be actually the perfect biomarker. But we would also not only know about the food, but the biomarkers can also be the bridge between food intake and the risk of chronic diseases. So biomarkers may explain why foods have specific health effects. And that is also something that we would like to know. So what is actually then a dietary biomarker? And there are a lot of different definitions. And this is one I found in one of the publications of a recent football project. Football was a consortium that was funded by the Joint Program Initiative, A Healthy Diet for a Healthy Life. We were not part of that, but I know the University of Oslo was part of a football project, and many different parts of Europe. So food intake biomarkers are defined as specific metabolites that reflect the consumption of one specific food or food group, show a clear time and dose response, and are ideally not present if a food has not been ingested. So let's look whether we can find this one. And of course, we have to not only the food intake biomarkers, but many different, and this is highlighted in this very nice scheme. We already have heard about the recovery biomarkers that are shown here, and the predictive biomarkers. We also have the biomarkers for nutritional status, and I would also like to show something about this one. And they are, of course, within the hierarchy of dietary assessment and disease development. So when we heard this, the last the definition that we have seen just before, then we already would like to have biomarkers that are present in biological samples after the ingestion of a certain food or food group, but not otherwise. So that means we would like to have specific biomarkers. We would like to have dose-response associations, and we also need reliable and valid measurement techniques. And this is actually summarized in this slide, and I would like to go through this a little bit. Not too much in detail, because I think this is rather theoretical for most of you who are not working on a daily basis with dietary biomarkers, and who would rely actually on laboratories serving them with this analytics. So what about the specificity? So that means that the biomarker should be associated with the intake of a specific food or food group, and other food groups should not contribute to the concentration of a biomarker. And of course we know that food is complex, and many nutrients are present in many different foods. So what we really have to look here is for food components that are specific for certain food groups. We would also have a biomarker that is not only present, or that cannot only be measured in studies that have been done in so-called metabolic wards, but that are also measurable under real-life conditions that most of you will have in their daily practice. So that means we will be able to measure them both in controlled feeding studies, in population-based cohorts, and they should be also see the effect when we use different tools for dietary assessment. And of course, this could be broadened even more because we know that we have already heard that these different tools of dietary assessment really assess different aspects and different sources of error. We also would not have one requirement for the biomarker is not only the specificity, but also the kinetics and dose-response associations. So we would like to know about the distribution volume, the maximum concentration, the time of the maximum concentration after intake, so all these pharmacological parameters that we know from pharmacological investigations. So when we measure a certain concentration, then this concentration in any biological specimen should reflect the intake of a certain food or the body status. And when we look actually to pharmacokinetics, so then we know that, for example, after taking a certain antihypertensive drug, we know which blood concentration we can expect after a while, because this is clearly described. But for foods, we do not know this very, very well. We know a little bit about, if we look, for example, for the glycemic index, that would be the concept actually that we also know about the increase in blood glucose after ingestion of a certain amount of carbohydrates. And so what we would apply is actually that we measure the so-called area under the curve after ingestion of a certain food. And the problem or the challenge in nutritional research is that the area under the curve virtually never starts at zero. So because we always have some baseline value of certain biomarkers. So in drug treatment, if we don't take a drug, we don't have a biomarker. But if you're starting to drink a certain type of juice, for example, that has a lot of flavonoids in it, even if you have been on a low flavonoid diet before, you will have some flavonoids in your blood or in your urine. I will later show an example for that. So what type of studies do we really need then? So we ideally, these biomarkers are tested at different doses and with sampling over time, so that we can know about or learn about the kinetics and the dose-response associations, like a proof of principle investigation. We would also have both. We need studies both under controlled conditions and studies under real-life conditions, like, for example, in cohorts. And we also have to establish the measurement techniques. I will not talk very much about that, because this is also a field on its own, and where we need a close collaboration between biochemists, chemists, and also engineers who are really in charge of these measurements. Biological sampling could be everything. The most common is blood or urine, but we also are more and more tend to, for example, see the importance of feces and the microbiota, of adipose tissue, or even like hair or teeth. I know, for example, that in the MUBAR study, they also collected some teeth of the children. For knowing, I actually don't know the specific question behind that, but I know that this has been collected. And then we can also ask, should we do an analysis per variable, so that we really have so-called single analysis or so-called multiplex analysis, and more we have this multiplexing analysis, so that we get information on whole groups of metabolites. And especially in the screening process for dietary biomarkers, we could either employ the targeted metabolomics or untargeted metabolomics. And there has been a lot of research actually in the last years for especially in untargeted metabolomics, and I will show a little bit also on the meaning of untargeted metabolomics in the field of nutrition research. So, but let's first one point that is very often forgotten, and this is repeatability. And here I'm not talking about the laboratory repeatability. I mean, this is also something that is quite important, that the laboratory can deliver results that are stable over time. And this is especially with minor metabolites and in untargeted metabolomics, this is not always the case. So this can be a challenge. But what I mean is, whether when we take a blood sample, for example, in a cohort analysis, whether this measurement that we take at a certain very random time point is really associated or is informative about the long-term exposure or the long-term situation. So the repeatability in this sense means the extent to which a repeated extraction and analysis of a marker would indicate the same value. And this is best described actually by the so-called intra-class correlation coefficient, the ICC. And unfortunately, there are several descriptions or several ways to calculate the ICC, but the most common is actually that we take into account the both between person and within person variability, and that we calculate then the ICC according to this formula. I know that nobody likes these statistical formulas, but and I promise it's the only one that I have in this. So what we calculate actually is that we calculate the between individual variance in divided by the total variance. And so we would this would result in values between 0 and 1, and just as a rough guideline for interpreting the ICC values. So a value of less than 0.4 would mean that there is a poor agreement. So these are biomarkers actually that we should not rely so much on. And these biomarkers usually also are very variable, and they can give, may not reflect the long-term situation in a certain person. Between 0.4 and 0.75, we would say it is a fair to good agreement, so this could be accepted. And an ICC exceeding 0.75 would indicate an excellent agreement between methods. So that is something that we have into account. This is very rarely reported. We have a lot of, because you then also need repeated sampling, and many people, or for many biomarkers, we do not have repeated sampling. So this is definitively something that we should take into account when interpreting dietary biomarkers. And what we also would like is that the biomarker is not only valid in the specific Norwegian cohort of patients or persons that we are investigating, but that could be also is relevant for other cohorts. So what we would like to have is that both other laboratories and other cohorts with maybe different dietary habits can find the same associations. We will not necessarily find the same amount, because this is actually something we would like to measure, but they should find the same associations. So we need also validation cohorts and validation studies. Okay, and a big breakthrough actually in measuring dietary biomarkers was the establishing of the so-called omics and the metabolomics approach. Very briefly, the omics approach is the collective characterization and quantification of pools of biological molecules that translate into structure, function, and dynamics of an organism or many organisms. And we distinguish between the genomics, the transcriptomics, the proteomics, and here we are in the field of metabolomics. And that means that we are looking at the comprehensive study of low molecular weight molecules. And these can be either from cells or culture media, or from in nutritional, more related to humans, in human urine or serum. It can be from the endogenous metabolism or from exogenous sources like drugs, toxins, microorganisms, or we are most interested then in the nutrients. And that means actually that we have a whole bunch of concentration ranges, like really from nanomolar to millimolar. This is several magnitudes of concentration ranges. Solubility, that means water soluble, fat soluble, polarity and volatility. So this is really a challenge to all chemical analysis and biochemical analysis. And the main difference is actually then when we apply this metabolomics approach, whether we have a so-called untargeted or targeted approach. So what is actually then the difference? So untargeted approach, metabolomics, is more related to the discovery of new biomarkers and is more hypothesis generating. So this is really, without a clear hypothesis, we really look into the material and look what we find. And you can imagine that this is quite, that you need a lot of chemical and biochemical knowledge for be able to interpreting this data. So there are not that many nutritionists working on that, but more biochemists and also engineers who are working, and this is mainly based on mass spectrometry methods. In targeted metabolomics, we are this is more hypothesis-driven. So this is also usually based on MSMS, with either gas chromatography or liquid chromatography, but there we know the components where we are looking for, and this is usually related to pathways, so that we want to measure different metabolites of a similar pathway, whether they are up or down regulated. And we usually do here an absolute quantification. If we just look on untargeted metabolomics, I would really very briefly have a look on that. So when we distinguish different workflows, so we start first with a profiling, and then with a compound identification, and with the, oops, that was too quick, and then with the interpretation of the results. And if we look further into these steps, then the profiling involves actually that we have theoretical ideas about the metabolites that can occur, that we try to measure them with as precisely as possible, and that we also look for differences between the control and the test sample. The compound identification, so we will get a lot of different peaks in the mass spectrometry spectra, and then we have to identify the compounds. And this is usually done with the help of so-called libraries, so that we have to look whether the same retention time and the same mass is referring to a certain compound. But this is not very, very unique. So a certain mass and a certain retention time can represent many, many different compounds, because we also have the stereoisomers, we have the other isomers, so there is a lot of noise in these data. And then the interpretation would also rely on libraries and the in silico analysis, so that we really can move on further to the next experiment. And we have different degrees of metabolite identification in this, and of course we are always aiming for the highest level, that we really have a validated identification with a reference standard and a confirmed structure. But very often we end up at one of these levels before, that we only know about the mass. And you see here how many components or molecules can be at the same retention time and the same mass within such metabolomic structures. So there are a lot of challenges related to untargeted metabolomics, and that's also why I'm not really focusing the next of my talk on the untargeted metabolomics. But it is a very exciting area, and we already have some knowledge that has been generated from these analyses, but there is more work to be done. Okay. So, which food groups are actually then of interest for food intake biomarkers? Well, of course, these are food groups that are notoriously misreported, either intendedly or unintendedly. So this could be, for example, added sugar, because all people know that added sugar is not good, so they would maybe misreport it, or they even don't recognize it. And it's also one of my research fields, alcohol, that is also usually misreported. But we also have food groups that are associated with health outcomes, mainly with disease, either negatively or positively, and this would be, for example, red meat, fish, vegetable, fruits, or whole grain products. And I will give some examples on these food groups. So let's start with the sugars. Well, the biomarkers of sugar intake, in first instance, we would think about, well, this is very difficult, because sugar is basically, that is glucose and fructose, if we look on sucrose, and this is really also endogenously synthesized, that is, we have gluconeogenesis, we have glycolysis, so this is so much in the core of our metabolism that it will be difficult to find a biomarker. However, there are some biomarkers present, and one biomarker is actually the excretion of sugars in the urine. This I already said, that sugars is misreported, it is related to obesity. So what are the biomarkers? And one biomarker was actually the urinary excretion of different sugars. So both fructose, glucose and sucrose are found in very small amounts in urine. And this data are actually taken from metabolic ward studies, and they show a very strong agreement between these excreted sugars in 24 hours urine and the reported or the measured sugar intake. Under real life, this is taken from the paper from Taveska published in 2008. So collection of 24-hour urines is a challenge. We all know about that if you have done that with your patients, you know that this can be a challenging experience. But this is one point, that the 24 hours urine may be a challenge, but it is also, of course, the correlation does not look that fine if we have single days reporting and single days measurements. So these are really based on the metabolic ward studies of several urines and several days of intake. And we have to note that the amounts excreted are rather low. So they are usually less than 100 milligrams a day, and in these 24 hours urine. So we also need sensitive methods for that. There's a very interesting, so that would be one option to measure added sugar or to calibrate added sugar intake also in population studies. But there's another very interesting method, and this is the so-called stable isotope ratio method. And this is something where you go back to chemistry. I know that most people also don't like that. Or that most nutritionists don't like that very strongly. So what we actually see is that most molecules or most atoms in nature occur in different stable isotopes. And usually the major isotope has an occurrence of more than 95%. So for carbon, for carbon 12, so this is 99%. So we have 1% that of carbon atoms that has one neutron in addition, and this is then carbon 13. And so what we can do actually is that we can measure, and this is already used in archaeology and also in ecology to find out about the age and the regional appearance of certain plants, whatever. And so measurement of these isotopes can result really in very clear data. And this is also in plants and also in animals. These molecules or these isotopes behave a little bit different, not very much, really a little bit, and this is called biological fractionation. So that means that plants would metabolize stronger the abundant isotope, so the C12, and some plants will therefore enrich or have lower concentration of the C13. And this is actually dependent of the photosynthetic capacity of different plants. And in biology, the photosynthetic pathways in different plants classify plants as either C3 or C4 plants. And this is shown in the next slide. And what you see here is actually that most plants are so-called C3 plants. And C3 plants distinguish very nicely from the C13 ratio. And this is the delta C13 value. And this is given in promille. And this is always negative data values. The data are actually negative because this is compared to a reference material, and because this has been investigated, or this method originates from geophysics. The reference material is limestone. And so all plants have negative values of around -20 or -18 or something like that. And we are really talking about differences in the promille area. So but what you see is that the C4 plants are distinct from the C3 plants. And while most plants are C3 plants, corn and sugarcane are C4 plants. So that means that if people are consuming added sugar based on corn or sugarcane, then we would expect a difference in the stable isotope ratio for C13. And this is actually, this actually has been investigated. So and especially in the US, almost all added sugar is from either sugarcane or corn, and these are both these C4 plants. And so then there are several reports now from the US that investigate the stable isotope ratio of C13 to sugar intake. And these data are actually very promising. So these stable isotope ratios of fingerstick blood were quite strongly associated with the reported intake of sugar and sugar-sweetened beverages in children and adolescents in several studies. Well, this is quite promising, but now comes the major disadvantage. In Europe, we are usually consuming sugar that is made of sugar beet, and the sugar beet is a C3 plant. So I doubt whether we can use this method in Europe. I would say this is. I have not seen actually data for the added sugar and this ratio in European populations, but I would doubt that this is possible to investigate. But it is we also have stable isotope ratios for nitrogen, and we could also do it for sulfurs. So there are options, and this is maybe a promising method, but more research is needed. Well, I would highlight another food group, and this is actually alcohol intake, or this is more or less another nutrient or anti-nutrient. And the problem with alcohol intake is that self-reported data on alcohol intake are quite unreliable. And we would really know about alcohol consumption of adolescents or even children, pregnant women or old adults. Problematic alcohol intake, that means high alcohol intake is associated with shame and taboo, so people do not report that actually. And we can, of course, measure blood alcohol concentration, but the blood alcohol concentration disappears after like 7-8 hours, and then it is no longer measurable. We could also measure established clinical variables like carbohydrate deficient transferrin, but this will only be changed after heavy alcohol consumption. But for example, in pregnant women, we would like to know even about, because there is no close dose response of alcohol intake in pregnancy and the fetal alcohol syndrome, we would like to know even about small amounts of alcohol. So we need new markers of that, and we actually, I was part of a study that evaluated new markers of alcohol intake, several new markers. So what we measured actually was alcohol intake in healthy volunteers, and I would call them semi-controlled conditions. Actually, these people were joining a party, and after the party we got blood and urine samples of them. So that was, at best, it was semi-controlled conditions. But actually we had a lot of fun, I must So we measured not only blood alcohol, but also markers that are called like fatty acid ethyl esters, ethyl glucuronide, and the ratio of hydroxytryptophan to hydroxyindolacetic acid, that are all metabolic pathways that are changed after alcohol intake. And we forced these, that are actually students, we forced them not to drink any alcohol during the next 4 days, and then we sampled blood and urine from these students. So that was an extended drinking experiment and blood sampling scheme. So this was more than 4 days, or more than 100 hours. And during the party, they consumed, on self-report, between 64 and 184 grams of ethanol. So some of them were quite drunk, actually, at the end of the party. But as I said, we had a lot of fun. But during the next days, these students were really quite coming back to our laboratory. And what we really have seen is that the ethanol disappeared very fast. The dotted line is the limit of quantification, so there was no alcohol present in any of the samples afterwards. We measured also the fatty acid ethyl esters, and we saw also a relatively strong decrease, and so that parameter was not really very informative after about a day. Then we measured also the urinary ratio of this hydroxytryptophan. These are all markers of, or these are all metabolites of tryptophan, and the enzyme activities are influenced by alcohol. So that was a little bit better, but not really very convincing. And the only convincing one was really the ethyl glucuronide. And there you see that this was, at least in some of the students, was even be measurable above the limit of quantification after 4 days. So that was really a promising marker, and of course we have not been the only ones who did studies like that. There are several laboratories that investigated the ethyl glucuronide concentrations, and so the conclusion was actually it was measurable for several days after moderate amounts of ethanol ingestion. It is specific and only detectable in urine after ethanol consumption. There is a theoretical chance to get false positive results if you really put a lot of alcohol on your skin. For example, in skin disinfection, or if you have microbiologic contamination of the urine. But this is more theoretical than in practical clinical practice. And the ethyl glucuronide is now introduced in clinical biochemistry and is also used to detect alcohol consumption in clinical routine. So this is quite a quite useful marker. I saw that I got a relative 5 minutes. Okay, I will try. Maybe we have to skip one of the examples. I don't know. Okay, so what these have been examples for targeted for targeted analysis. It was not even metabolomics, because it was not really comprehensive analysis of low molecular weight molecules. But it was also limited to food or nutrients that had a very simple structure. And we know that most foods that we consume is not that simple. It's not like alcohol or not like sugar that is mainly based on one highly refined molecule. So we have most food that we eat are much more complex. And one nice example for complex food is fruit and different fruits. And actually I borrowed from Bergen a very nice slide that shows dietary complexity that is shown here. So you see that we have both the nutrients, the different foods, but not that can be grouped into food groups or food products, food groups, and then or even in dietary pattern. And if we look then on fruit, we also have many different fruit, and it was a little bit by chance that the blueberries were just on the top, because I would like to present a very nice study on blueberries actually. So blueberries have been a very good how do you say that? Rückte? Sometimes I miss the English words, and then only the Norwegian words come into my head. But okay. Reputation, yes, thank you. But they are really a very complex food. So they contain more than different flavonoids, and and they can be in the body. These flavonoids are even metabolized and then excreted in the urine. And the most abundant flavonoids are in blueberries are the anthocyanins that are represented here by 4 different structures, but there are even more. So and we know that flavonoids have properties that they may reduce blood pressure, that they may act as an antioxidative. So they are good reasons to measure actually the flavonoids associated with blueberry intake. And I found a very nice study actually that I think was also done in the US. So they had healthy volunteers. It reminded me actually on our alcohol study, but I think they did not have so much fun. So what they did is that they have 5 times 24-hour urine collections in 17 volunteers. So that resulted in 626 urine samples. And they measured then the anthocyanins in these urine samples. And the intervention was that these 17 people, got 250 milliliters blueberry juice every day. And then they looked whether the blueberries juice consumption would increase the anthocyanidin excretion. And the result is actually, yes, it did. But here you also see the problem or the challenge, but you never go to zero. So this was the urine after the washout period, but you still see that there is substantial excretion of the different anthocyanins in clean urine. And then they consumed the blueberry juice, and you see that the different classes of anthocyanins increased quite a lot. So they identified 55 major anthocyanins and more than 300 minor. And the 300 minor are summarized here, and these are parts of the major anthocyanins. And as I said, we usually do not only have the aglycone, but we have metabolized products, and they can be excreted either as glucuronides or as methyl glucuronides, or even as the parent compound. And you see that we also see a nice increase after the blueberry consumption, but we do not start from zero. So the conclusion here, and this is a very nice example, I think, for targeted metabolomics, that we really looked into this urine compound, or this anthocyanins from the blueberry juice in the urine, and try to find also the association with the blueberry intake. I think I should stop now. Okay. Okay, then I have to skip a number of slides, but it doesn't matter. I would have liked to show you more examples, actually, also from our own research, but we will skip them, and I will come to my conclusion, and this goes very quick. So 2 slides. Okay. So what are then the challenges in the dietary biomarkers? So most of the biomarkers that I have presented, or that I would have liked to present, are not available in routine laboratories. So if you are working in a hospital and you are looking that you would like to have biomarkers to support your dietary assessment, you will not have access to these measurements. And this will probably stay like that for a quite long time. And some of them may never be in routine laboratory. The ethyl glucuronide for the alcohol consumption is here an exception. At least here at Haukeland we are offering this marker. And we also need more data for most biomarkers on the validity, on specificity and sensitivity, dose response associations, and last not least, the repeatability or the interclass correlation coefficient. And I would like to conclude, not with my own words, but with the viewpoint by Frank Hu and Walter Willett from last November. Objective biomarkers, such as blood levels of fatty acids and carotenoids and so on, have a potential to improve the accuracy of dietary assessment and are an active area of research in nutritional epidemiology. However, considering the limitations, new biomarkers or technologies are likely to complement rather than replace self-reported dietary assessment tools. Thank you for your attention.